When you look at Mars, the first thing you notice is the color. It looks like a world of fire. But that signature red is actually a fine layer of iron oxide rust covering the rocks and soil. While dominant in the night sky, Mars is relatively small, roughly half the size of Earth. Despite that smaller scale, it holds the solar system's absolute record for the most extreme geography. This is Olympus Mons. It stands 15 miles high, which is nearly 3 times the height of Mount Everest. Then there is the Valles Marineris. This canyon system stretches 2,800 miles across the crust, long enough to span the entire continental United States. Mars is a world of physical contradictions. It's significantly smaller than Earth, yet it hosts geological features at a scale we simply don't see on our own planet. Exploring those features today means contending with a barren desert. The current climate is brutally cold, with an average temperature of -63 degrees Celsius. But the landscape is scarred with evidence of a different era. About 3 billion years ago, liquid water was plentiful here, creating the massive flood-carved canyons and river meanders we see today. This creates a central mystery. By understanding how this wet world became a frozen wasteland, we can better model the forces that drive the evolution of Earth's own climate. To solve that climate mystery, we've spent decades deploying a robotic armada to investigate the surface. In 1976, the Viking landers gave us our first look from the ground. They used a robotic arm to scoop up soil and test it, but because they were stationary, they could only analyze the immediate area around their legs. That changed in 1997, when the Pathfinder mission released Sojourner, a rover that moved between targets, like this rock nicknamed Yogi, to conduct geological fieldwork across different terrains. Switching from stationary landers to mobile rovers was a breakthrough. It allowed us to stop waiting for data to come to us and start actively following the trail of Mars' geological history. In 2004, 2 more rovers, Spirit and Opportunity, arrived with a specific objective: find irrefutable proof that liquid water once existed on the surface. They found proof in the rocks themselves. These are conglomerate rocks, formed when pebbles cement together. Looking closely at the 1 centimeter scale marker, you can see these pebbles are smooth and rounded, a shape that only occurs when rocks are tumbled by a fast-flowing river. Building on that discovery, the Mars Science Laboratory, or Curiosity, landed in 2012. This rover is the size of a car and carries a much more sophisticated suite of instruments. Curiosity is a roving analytical lab. It drills into rocks for organics, measures the local atmospheric gases, and tracks dangerous surface radiation. These missions have turned a distant light in the sky into a mapped and documented world, providing the specific data needed to plan for what comes next. This data is directly relevant to our survival. By comparing the extreme climate history of Mars to our own, we can build more accurate models of how planetary atmospheres collapse or stabilize over time. The rovers also provide the exact environmental baselines required for human safety. The radiation data Curiosity collects on the surface is the primary dataset engineers use to determine how much shielding future explorers will need. These measurements are the blueprints for our first outposts. They allow us to engineer self-contained structures that can specifically protect humans from the thin atmosphere and the solar radiation detected on the surface. Decades of robotic exploration have done more than solve the mystery of ancient water. They have scouted the terrain and identified the hazards, preparing the way for the first human footprints on the Martian frontier.